alcohol is esterification reaction. Carboxylic acid. Can you guys who I'm talking mute yourself? There are so many of you talking. Mute yourself. About 9 grams per 100 ml. Then, but as if you look at the alkyl group, as the alkyl groups increase, will reduce. As the alkyl group increases, so the question is that the smaller the size of the alcohol, the better its solubility of water. So,
I said this guy is mad.
Mute yourself. What the fuck is wrong?
The national head of the
because of us.
So now I guess you guys can see my. Can you see my slide? No. Can you see my slide? No.
Yes, yes, sir. Yes, sir.
Okay, good. So I'm just going to have to manage through this class. So, you know, our compounds that have the hydroxyl group on benzene. So if you can see my cursor, you can see the OH on benzene rings. So that's phenol. So whether it's the smallest one, phenol, or this second one that you see here, also phenol. So this is phenol, this molecule is phenol. Can you guys mute yourself? When you log into a class, you mute yourself. Mute yourself. Now, so you see that this is phenol, the simplest compound in that family. So so you can now have the phenol having any other atom that is not hydrogen, so or a group. In this case, you have a phenyl group attached to phenol, and the position is, if position 1 is this position 1, this is the ortho position. 2 position to it. This position will normally be meta. This position will be para. So in this case, you have an orthophenyl phenol. So won't worry so much about this big one. This is also a phenol substrate, but it has another big molecule attached to it. So phenols, well, they said the original name was phenol. I don't think we want to bother so much about this. What is so important on this slide is that, again, this is phenol. Benzene ring with OH makes it phenol, and then it has a substituent, which is a CH3, a methyl group. In numbering, if you are going to number, this is position 1, where here you have the OH group. So you number in the direction that will give the substituent the smallest number possible. So you have to number 1, 2, 3. You don't go this other way. If you number this other way, you go 1, 2, 3, 4, 5, which is 1. But when we have this kind of arrangement, this is usually the ortho position meta. So metaphenols, so methyl phenols are usually called cresol. It's just a common name. This is another phenol compound. Again, benzene ring with OH, phenol. It has two nitro groups. This is an ortho and para, or 2,4 dinitro phenol. 2,4 dinitro phenol. So in naming phenols, well, it's the hydroxybenzene are normally called phenol, and then if they have substituents at locations, you can begin to distinguish which one is the ortho position, the methyl position, or the para position. And so that's what this slide is talking about. So you can have substituted methyl phenols are called cresols. It's just a general name. You may have other, okay, these are other substituted phenols. So this is the main phenol compound. This is a paramethyl phenol. Common name is cresol, paracresol. Methyl phenols are called cresols, but the location is para position. That is why it's paracresol. This is orthocresol, for example. This is meta position. The position is, this is ortho position, meta position. The three position is meta position. This is another, this is a phenol compound because OH on benzene, this makes it phenol. This will be a substituent. This one too will be a substituent. So what are the locations? On position 2, you have a chloro atom. On position 4, you have a benzyl group. A benzyl group. So that is why it's a 2-chloro 4-benzyl phenol. The same thing here. This is a phenol compound, OH on benzene. This will be a substituent. This is another substituent. So in the 3 position, you have a nitro. In the 4 position, you have an ethyl. But when you are going to name it, you have to arrange them alphabetically. The ethyl comes before the nitro. That's why it's a 4-ethyl, 3-nitro phenol. In terms of synthesis of phenols, you can prepare phenols from cumin. So, and what's cumin? Cumin is when you have a propyl group on benzene. This is phenol, cumin. Propyl group, this is 1, 2, 3 carbon alkane, propane. Because it's attached in the middle, it makes it phenyl 2-propane. It's called cumin. That's the common name. Now you can oxidize cumin to give cumin hydroperoxide. So this hydrogen here is oxidized, cumin hydroperoxide. When you now hydrolyze cumin hydroperoxide, it cleaves into 2 compounds. You get a phenol and acetone, which is acetone is an important solvent. Phenol too is also important. So you can prepare phenols from cumin, and it's an important industrial pathway to make phenol. You take cumin, you oxidize it, you get cumin hydroperoxide. You now hydrolyze the hydroperoxide into phenol and acetone. These are some other synthesis of phenol from diazonium salt. If you take aniline, benzene with NH2 is aniline. You can diazotize aniline using HCl and sodium nitrite. Diazotization. If you take aniline, you subject it to HCl and sodium nitrite. You get diazonium salt. When you now hydrolyze the diazonium salt, you convert it to phenol. Another method for preparing phenol is using benzene sulfonic acid. If you take benzene sulfonic acid, you subject it to sodium hydroxide, and at high temperature, you get the sulfonate. The sulfonate you can now hydrolyze. It will replace the ONA with OH. So this is another method for preparing phenol. Phenols are generally acidic. Just like alcohols that have OH functional group. Alcohols are not acidic. They tend to be more of neutral compounds. But phenols also have OH group. They tend to be more acidic than alcohols. So if you look at the pK it's about 10, while the one for alcohols is about 16. So the lower the pK, the more acidic. So phenols react with sodium hydroxide solution, alcohols will not. So, and if you look at this scheme here, you can see phenol with sodium hydroxide. The Na, the sodium metal, can substitute the hydrogen to give you the sodium phenoxide. This is a phenoxide. Phenol with the oxygen is called negative, it's called phenoxide ion. So when you react phenol with sodium hydroxide, this sodium hydroxide can substitute the hydrogen to give you the sodium phenoxide and water. This kind of reaction is not possible with an alcohol. You can only get the alkoxide if it was an alcohol, if you use a strong metal, a strong active metal like sodium metal, sodium hydride, potassium, magnesium. All those ones will substitute the hydrogen. So now, in terms of, we already said that phenols are acidic, but again, the substitution on the ring can impact the acidity of phenol. Let me point out that when we say something is acidic, it means that it can donate a proton H+. So if you look at this again, if I use this, the OH on benzene, this is phenol, it is acidic because it can ionize. When we talk about strong acid and weak acid, we say the strong acid are acid that can ionize almost fully. Listen to now. The point is now is that substitution on the benzene ring can impact the acidity. If you have a group on the benzene ring, electron donating group pushes electron to the ring. Now, how does that electron withdrawing affect it? You know that the OH here, although they are not showing the hydrogen. Hello? Can you hear me? Hello, I hope you are hearing me. Dixon. Hello? I hope you can hear me. Dixon.
Yes, sir. Can hear you, sir.
Can you hear me? I hope you are
yes,
hearing
sir,
me.
we can hear you, sir.
Okay, yeah. Okay, thank you. I'm just now. So what I'm saying is that we say a phenol is acidic because it can ionize and therefore liberate the H+ and the O-. So, but the point is, when the benzene ring is substituted, the substituent will influence the OH functionality. If it is pulling electrons away, because oxygen and hydrogen are sharing a bond. If you pull electrons away from oxygen, it will pull the electrons it is sharing with hydrogen and therefore push the hydrogen away as H+. But if the oxygen is richer in electrons, it will not want to take the electron pair is sharing with the hydrogen, and therefore it will be reluctant to push the H away as H+. The implication of this is that if you have an electron withdrawing group pulling electrons away from the oxygen, because the group here is pulling electrons towards itself, it was going to make this oxygen want to remove electrons that is sharing with the hydrogen, and therefore it will push it out as H+. That it will increase acidity. But if you have a group that is pushing electrons towards oxygen, it will not take the electrons it is sharing with the H, and therefore will stay. And that is how
like that.
electron withdrawing group and electron donating group. So an electron withdrawing group will be acidity
So like
because it's able to stabilize
they call you as if
the phenoxide group. While an electron donating group will decrease the acidity.
You're not supporting my
Of course, because
and when you find
this one is having
and you know anybody
mute yourself.
because it doesn't sound
Students,
like are you taking me seriously? But tell are you
mute yourself.
not looking for virtual assistant.
Yes, like they brought it back.
Now, even if you are software manager, you will
Now,
probably
so the other thing is also that what we're saying is that nitro group, for example, is an electron withdrawing group. If you look at this nitro group, it makes the electrons to come towards it.
Apart from like the actual
It has positive charge, so electrons will come in this direction. So the implication is that electrons will also move down. You can see the electrons are moving away from the oxygen, and therefore it will increase the acidity. So it's like an electron withdrawing group here. Electron withdrawing group will increase acidity and make the H to go off as H plus. So some of the reactions of phenols, when you compare them to alcohol, an alcohol, for example, it can react with hydrogen halide acid, but phenols will not react with them. Phosphorus like halide. Alcohol
No.
I don't know why this was not working.
Sorry, we cannot hear you, sir. We can't hear you, sir.
Hello, can you hear me now?
Yes, sir, we can hear you now.
Okay, then okay, I know that once I mute everybody, then I'll unmute myself. So some people are still making noise. Okay, let me just continue. Now, so what I was saying is that phenols can react with active metals. The same thing, alcohols too can react with active metals. So the sodium metal here can replace the H as sodium phenoxide. And in terms of acidity, if you compare some different types of compounds, usually these are good exam questions. You know, sometimes they can give you an alkane, they give you an alkane, give you an alkyne, give you an alcohol, give you phenol, give you an carboxylic acid, and let's say arrange them in increasing or decreasing order of acidity. This scheme, just get familiar with it. An alkane, for example, cannot behave like an acid. But if you compare an alkyne, this is a terminal carbon hydrogen bond. The terminal alkynes, you should have been told that the hydrogen of the terminal alkyne is acidic. Alcohols also can behave as mild acid, very, very mild acid, because they can protonate in some reactions. Phenols are stronger acids than alcohols, while carboxylic acid are stronger than phenols. So again, this is reaction of, just as phenols can react with active metals, phenol can also react with sodium hydroxide to form sodium phenoxide. Alcohols cannot react with sodium hydroxide. Some other reactions of phenols They can form an ester. So you have phenol. This is methyl, orthomethyl phenol. That is autocresol. We said that methyl phenols have the common name of cresol. So this is autocresol. You can react with this carboxylic acid to form the ester. No, so because the OH is behaving as if it's like an hydroxy group of an alcohol, that's why it can react with carboxylic acid to form an ester. Again, this is salicylic acid with acetic anhydride. You can also have, this is an acid derivative. This is acid. So the acetic anhydride will only react with the OH, not with this one. That's why you have the, and this is aspirin, which is an important analgesic. Now, phenols can also react to form ethers. So if you take your phenol, react it with an active metal, you get sodium phenoxide. This active metal can replace this. You now bring an alkyl halide. So this is your sodium phenoxide, ARO. The halogen R will replace its position. So you can see this is an ether. This is called Williamson ether synthesis. Williamson ether synthesis. Again, this is another example of it. You have, this is paracresol. If you remember, para position to the OH, paracresol with an alkyl halide in presence of sodium hydroxide. Sodium hydroxide will displace the hydrogen here to form the sodium phenoxide, and then the halogen will take the sodium as NaBr, while the alkyl group will come and replace it to form the ether. So this is an ether. RORs or ARORs are ethers. So other reactions of phenols again is when they form dyes, and that is through a coupling reaction. To carry out this coupling reaction, you need to get a benzene diazonium chloride. This small compound is prepared from aniline. When you have benzene with NH2, that on it, you can diazotize benzene that has NH2 using sodium nitrite in conc HCl. It will give you the benzene diazonium chloride. The benzene diazonium chloride, you cannot react it with the phenol. It will always, whenever you have this reaction of a phenol or a substituted phenol with benzene diazonium chloride, the nitrogen will always come and react at the para position. So you can see it. And this is structure of a typical dye. Normally, this will have colors. And by changing the substituent on the ring, it will give you different type of colors. So some of the colors that you see they use to dye cloths are actually azo dyes. And this is the process by which they prepare these azo dyes. You get your phenolic compound, you get your benzene diazonium chloride that has different substituents which can give you different colors. When you carry out this reaction, it's going to be a coupling reaction. And therefore, the reaction will always occur at the para position to give you the dye. So when I talked about oxidation earlier, it does actually show some. So if you take phenol and then you react it with Fremin salt, potassium nitroso sulfite, so you can see it can oxidize it, phenol, into a quinone. It introduces a new oxygen group here. So phenol gets oxidized to a quinone. So this one is benzoquinone, double bond O, double bond O. Phenol, you oxidize it to a quinone compound, but this one is benzoquinone. The quinone, when you get quinone, you can actually hydrolyze it. So you can reduce it using thin chloride in water. It reduces the this keto compounds or the keto groups into hydroxyl group. So you can go from benzoquinone to hydroquinone. You can go from benzoquinone to hydroquinone. And what's the scheme again? You take phenol, you oxidize phenol to benzoquinone. Then you can go from benzoquinone to hydroquinone. Well, this one is, I think, is not so important. It's just showing that a type of benzoquinone, a benzoquinone moiety that has an isoprene attached to it. It's just showing an example of a benzoquine. Some other, I think, uses of phenol at this point. Phenol is used as an antiseptic. A lot of these antiseptic they use to clean the toilets, to disinfect content phenol. It's used in some cosmetics. It's used in some health interventions, and maybe it's used in colors, because when you are able to react it to form an azo dye, you can convert it to colors that is used to dye cloths. So this is the last slide on phenols. So let me quickly go to the last material I want to share. So I'm going back here. Alcohols. Now, ether. Okay. So ethers. So ethers are compounds that have ROR, alkyl group, oxygen group, alkyl group. So it may be ROR, it may be aryl oxygen alkyl, it may be aryl oxygen aryl. So it can be an aromatic compound, aromatic group or an alkyl group. So the ethers generally have less polarity compared to alcohols. Alcohols have OH group, which is a polar molecule. So alcohols have the hydroxyl group, which is polar. It's polar because you have a bond between oxygen and hydrogen, and the electron in the bond between the oxygen and hydrogen are not equally shared. The electrons tend to be more with the oxygen than the hydrogen. That's why alcohol very flammable. So in terms of nomenclature, naming ethers, you know that ethers tend to have an alkyl group, oxygen in the middle, and an alkyl group. So you can name them by naming the alkyl groups followed by ether. That is, you list each of the alkyl group with a YL ending and then add ether. So that's why if you look at this first one, this is a methyl group, another methyl group. So methyl and methyl is dimethyl and ether. So we name this, and then add ether. The same thing. This is a methyl group. This is a ethyl group. That's why ethyl is ether. The small one first, then the big one. If you look at this one again, this is an ethyl group. This is a chloromethyl group. So the chloromethyl is, kind of smaller. So we just looked at is when you just name the alkyl groups followed by ether. You can also name them by naming shortest carbon chain with an oxy ending. If I go back here, what we are saying is that if you look at this one in the middle, this is CH3O. This is the smaller one. Methyl is smaller than ethyl. So you can name it using the smaller one with the oxygen. This will be a methoxy ether. So when you use that approach, you name the shortest carbon chain with an oxy ending. That's why I said methoxy. And then you number the location of the ether bond on the long chain so that it is as low as possible. So let's look at when you use that other rule. So this is that second rule. In this second rule, this is the shorter chain. This is the longer chain. So you add the oxygen to the shorter chain. That is why it's a methoxy. You can see it. So methoxy. So you've taken the entire thing. What is left is propane. So, and it's on the one position of the propane. This is carbon 1, carbon 2 of the longer one. So the methoxy is on carbon 1. That is why it's 1 methoxy propane. So you look at it again here. This is the smaller one. That's why it still takes the oxygen, methoxy. And then this is a chloroethane. Chloroethane. Again, this methoxy is on carbon 1. The chloro is on carbon 1. That is why it's 1 chloro, 1 methoxy ethane. So you see, we have looked at two ways of naming ethers. The first one is when you name the alkyl and add ether. This second nomenclature is when you look at the smaller chain, add the oxygen to the smaller chain and call it an alkoxy, like the alcohol. So this will be a methoxy. This one will be, for example, this third one will be 3 carbon alkanes, 1, 2, 3 is propane. With the oxygen is propoxy. And then the oxygen is on carbon what? Carbon 2 of the butane. The oxygen is attached to carbon 2. This is butane, 4 carbon. So it is a 2-propoxy butane. 2-propoxy butane. So again, this is chloroethoxy. Chloroethoxy, in which position? Now this OH makes this butanol. This is position 1, position 2, position 3. So you can see 3. So that is on position 3, you have this 2-chloroethoxy. On position 3, you have 2-chloroethoxy and then 1 butanol. So those are two methods of naming ethers. The other thing that I think is important in this slide, because of time, is that when you have an ether, you have an alkyl, oxygen, alkyl. The molecule is not 180 degrees straight. It actually is a bent molecule. The structure is bent. You can see it's bent here, it's bent here. Now, because the oxygen is a little bit to one side, the alkyl groups are to one side. This gives ethers a slight dipole moment. Oxygen atoms gives ethers a slight dipole moment. It is not a straight molecule. It is a bent molecule. The oxygen is a little bit to one side. The alkyl groups are to one side. So what tends to happen is that you find you are going to have a net negative charge in this direction where the oxygen is, where they are going to have a net positive charge where the alkyl groups are. That is the slight dipole that it has. So I just said we need to point this one out. These are some examples of ethers as well. Para-dimethoxy benzene. This is benzene ring, has oxygen, R. So there's an ether here. There's an ether here. That's why it's a para-dimethoxy benzene. This is a methoxy. These are in para position, and they are dimethoxy benzene. This is synthesis of ether using an alkyl halide and an alcohol. So you first of all react the alcohol with the strong acid, you protonate it, then it's you have this elimination, and then the second molecule of the alcohol now reacts with the carbonium carbon here. When this OH2 goes as water, it's going to generate a carbonium carbon here, so that the negative electrons on the second alcohol molecule can now react with it, and you get this. Subsequently, it loses a proton and you get an ether. So this is just a method of preparing ethers from alcohols when you catalyze it with an acid. This is preparation of ethers from alcohol when you catalyze by an acid. Look at the reaction again. The acid first of all protonates the OH of the first alcohol molecule to form the OH2 plus. There's an elimination of water. You generate a carbonium carbon here. The second molecule of the alcohol now attacks the carbonium carbon to give you this intermediate, from which you now lose a proton and you get your ether. This is an example of Williamson ether synthesis. You are using like a cyclic alcohol, cyclopenthenol. You are using a strong acid, base, sodium hydride. Now, because it is a strong metal, it's able to substitute the hydrogen here to give you this alkoxide. You know, the sodium metal replaces the hydrogen. The sodium metal well, I hope you can still see my slide because I'm using my phone. They've taken like where I am. Yeah, now wow. Hello, can you? Hello.
Yes, sir. We can see the slide.
Okay, you are seeing my slide. So okay, so you can now. So yeah, so this is a method of Williamson ether synthesis. The sodium hydride reacts with the alcohol of the cyclic alcohol, and then you form the alkoxide, and then basically you come alkoxide, you bring your alkyl halide. What's going on? So can you still see my slide?
No.
You can't see it. It says I've lost my whole slide. Let's see. Okay. I'm coming. Let me see that quickly. Hotspot. Just hold on. I'll switch. I want to hotspot on my laptop. Techno. Yeah, come on. Yeah. Oh, the light is back. Hello. What's going on? Hello, I think my slide is back. Hello.
Yes, sir.
Okay, all right. So let me just wrap up. So Move it to. Yeah, so the cyclic alcohol with a strong metal, sodium metal, sodium hydride, any active metal will convert it to an alkoxide by replacing the hydrogen here. You now bring your alkyl halide. So the sodium will take the halogen to form NaI, while the methyl group will come and replace it here to form your ether. So that's cyclopentyl methyl ether. This is also just like you can use sodium hydride and the alkyl halide, you can also use silver oxide. You can also use silver oxide with alkyl halide. It will do the same thing. It can replace the silver, can replace the hydrogens of the oxygen group, and then you now react it with the alkyl halide. That's what has happened here. The silver metal has replaced all the hydrogen, and then once you've done that, you now bring your alkyl halide. It will now replace the silver, the metal, so that you now have this ether. You can say all these are ether groups, ether, by reaction of the CH3I and silver oxide. Now some reactions of so some reactions of I hope I'm still sharing my slides. Yeah, some reactions of ether. If you react an ether, ethers are generally unreactive. However, they can be cleaved. You can break the bond using a very strong acid. So at elevated temperature. So when you are using HI, HBr, etc., and you heat them at reflux temperature, it's able to cleave the bond to give you the phenol back and the alkyl halide. So you see phenol, this phenyl ethyl ether, phenyl ethyl ether. But of course, if you are going to name it, the ethyl is smaller than the phenyl, so that's why it's ether, phenyl, ether. If you react this with a strong acid at high temperature, it's going to cleave it to give you your phenol and your alkyl halide. So this is just showing the mechanism here. Because you are using a strong acid, it first of all protonates the oxygen of the ether. Then you have a cleavage, and then to give you the alcohol functionality, and then the halogen comes to the carbonium carbon here to give you the alkyl halide. So basically, whether it's an aromatic molecule or an aliphatic ether, you can cleave it using a strong acid at high temperature into the phenol and alkyl halide, or into an alcohol and an alcohol. These are cyclic ethers. These are just examples of cyclic ethers. This 1,4-dioxane. These are solvents. Both 1,4-dioxane and tetrahydrofuran. They are just solvents. They are usually used as solvents. Cyclic ethers behave like acyclic ethers, except if the ring is 3 members. So this is dioxane. This is THF. It's popularly called THF. THF. Tetrahydrofuran. But they are solvents. Now this is also a small 3-membered ring ether, ethylene oxide, which can be prepared from ethylene. This is ethylene. When you react ethene, silver oxide, and oxygen at high temperature, it forms a bridge oxygen here. This is ethylene oxide. This is called ethylene oxide. So this is normally used, or sometimes also called oxirane. Oxirane. This is oxirane here, but it's ethylene oxide. 1,2-epoxy ethane. 1,2 ethane, 1,2-epoxy ethane. The ethylene oxide can be prepared when you have a carbon-carbon double bond and alkene functionality. If I go back here, you can see it's an alkene functionality with oxygen. You form the epoxide. So apart from using silver, you can also use perbenzoic acid. This is this is carbonyl C-double-O-O-O. This is per acid. It's called like when you react a per acid with a carbon-carbon double bond, it's able to bridge it. It introduces one of the oxygen to the carbon-carbon double bond to form an epoxide. And then you have a carboxylic acid back. So if you look at this scheme, this is a cycloheptene. The reaction occurs around the carbon-carbon double bond. It reacts with the per acid. It introduces one of the oxygen here to form the epoxide. And then it is reduced by one, so that's why you have a benzoic acid. Another reaction